Okay, so for lab today, what we're going to do is, since I have to make up some of these lectures and stuff, I'm going to make the lab kind of a combination lecture kind of lab. We're going to kind of do like some hands, I'll mention some stuff. You can measure some things. We're going to kind of go back and forth just to kind of merge the two together. And I think we can get caught up really fast. So what we want to do is I want to start looking at the microscopic aspect of kind of the circuits. I want to start with that. Then I want to show you how then it can apply to what we can do with it. And it's kind of neat. Let's see if I got it right. Okay, I think I got that right. I think I put you right. Okay, is that you?
Yeah.
I did. Okay, got it. Very good. So what I want to do is we want to start looking at circuits. And we're going to look at what are called DC circuits. Okay, this DC is going to stand for what? Well, you tell me what does DC stand for? That's going to be direct current. And I'll explain what that means in a second. That's basically going to be that current's going in one direction, but I haven't defined the word current yet. So let's go from there. So what I'm going to do is I'm going to draw a piece of, let's do a little review first. If we had two plates like this, if I put a positive charge here and a negative charge here, remember I had a battery here. How do we say the electric field goes? It goes from positive to negative, it goes like this. That's our electric field. This is E. And in case of two parallel plates, what do we know about that electric field? That electric field is a constant. And so if we wanted the voltage difference here, okay, how do we say we found the voltage difference? This is what happens when we haven't had class in 3 days. And the room was 512 degrees. Okay. There's a minus sign. What? Okay, we had the change in the electric potential energy over the charge moving. Good. Well, we beat on that, and we could also write that as it had a minus sign, an integral of this E dot dl. And what did that dl represent? See, if it's this bad already, imagine what's going to happen after spring break. It's going to be, who are you? What did you do with my students? Remember, we had a path connecting the two. So we had some path connecting the two regions here. And the dl is going to be, if I look at that path, what does that dl represent?
A small length of it.
And it's always tangent to that path here. So it's a small length, just like Mark said. And dl is always going to be tangent like that. And that here's our electric field. So in this case here, what do we get? We get this minus integral from some initial to final spot, magnitude of E, magnitude of dl, cosine. What angle does the E make with the dl there? 0. Cosine of 0 is 1. Now, what can I do with that electric field? I can pull it out. So I can write this as minus E, integral from the initial to final spot of this dl of this. And if I take the little dl and add them all up, what do I get? We get the separation distance here, which would be L. I think we're calling it D before. I think we're calling it. Although we're going to switch it to L right away. So in this case, I'm going to call this distance here. I'll call this L like that. So it's going to be this minus integral E L. This L here, L is the distance between the plates. Okay, so just keep this in the back of your head. This change in voltage is this minus E L. Keep that somewhere in the back of your head. We're going to come back and use it in just a second. That makes sense? Now, what I want to do is I want to apply these ideas to basically an actual circuit. So let's see what we can do with this. My circuit is going to be this. I'm going to have a wire here like this. This has some cross-sectional area here, A. So A is the cross-sectional area of the wire. It's going to have some length L. And I'm going to put a battery here like this. So here's my wire, like that. Now, what did we say that battery is going to do? That battery is going to be a source of a what? That it's going to ultimately be a source of current, but we don't know that yet. Back up. Batteries produce an electric field in the wire. So I'm going to draw my little electric field like this. And actually, it's going to go all the way through here like that. So if you're the little electron here, what's going to happen? Let's make that look more like an electron. What will you do if you're an electron there? What will be the force on you? If the electric field is going this way. So here's our electric field. So the electric field is going this way. What would be the force on the electron? Assuming you're going the other way, it's going to want to go through this positive end. So this electron is going to go like this. It's going to go this way. Hop on the battery here. Then some incomprehensible chemistry takes over, kicks it to this side here. And the electron is just going to go like this. Okay? That makes sense? Now, what we're going to say is, if you look at all these electrons, then, right, so we have an electron here, we have an electron here, one here, one here. We have electrons all over the place. So all these electrons are going to have a force on them. Moving them this way, they're going to go like this, hop across here, go like this, and these electrons are just going to go like this all their life. The motion of that charge there, we're going to call current. So motion. Electric charge in the wire. It's called current. We always use I for current. And this is how we're going to define current. Current is going to be, by definition, the following. I'm going to imagine, I'll draw the little wire over here. Here's like a little line like this. There's going to be a certain amount of charge that goes this way. So this is my charge. I'll call that delta Q. So that's how much charge that moves past this little line. And how much time does it take to move for this charge to move across here? I'm going to call that delta T. So the time it takes the charge delta Q to cross the imaginary line is delta T. So we're going to say delta Q over delta T. That's going to be my current. And what do you think we're going to do to delta T? The limit as other way around, delta T goes to 0. Hey, what's that the definition of that? If I have If I say the current is the limit, this delta T equals to 0 of this. So I have this wire. And what do? I have this imaginary line. There's going to be a certain amount of charge here that crosses that little line. It's a tiny little amount of time. We call that A. And you're all pros at this. Every one of you know exactly what this is. You're collectively reaching into my chest and grabbing my heart and starting to squeeze it tighter and tighter and tighter. I can feel my chest getting tight now. The blood is starting to not circulate to my brain, to my extremities. It'll start turning blue soon, passing out, whacking my head on the table. Then I'm about to fall to my death. That's right, it's a derivative. Excellent. Good job. This is the definition of a derivative. dq dt. So your current is by definition dq dt. Let's get the units for this. Okay, what do we measure dq in? If it's charge. Coulombs. What do we measure time in? Seconds. So we have a coulomb per second. A coulomb per second is by definition an amp. So we measure current in terms of amps. Okay. Now, the odd thing is what are you going to measure? What device do you use to measure current?
Yeah.
An ammeter. There's no P in amp meter. That's to me just always seemed evil. I would call it an amp meter, but it's not. You drop the P, you call it an am meter. Okay. That's just the way it is. Any questions about that? So what I want to do is I want to look at the microscopic theory of what's going on here. Once we get the microscopic theory understood, we can start making things with these. But I want to get the microscopic theory because it turns out to be important. Oh, incidentally, what was their homework due? Tomorrow? Okay, you guys good with that, or do you need like another day for it?
We have like one more day. Do one
That was awfully fast. Okay, but I can extend it to Wednesday. Okay, so I have the homework due on Wednesday. Okay. So let's look at the microscopic theory. For motion. Okay, the first thing we do something really bizarre. We do this historically, and it's just weird, and you just have to get used to it. How? Let's ask you which direction. This current flow. Wire. Just the answer I'm going to give you is stupid, and again, it's just historic, but it's the way you have to just deal with it. And so let's draw a little wire again like this. We're going to be drawing this an awful lot. Okay, what did we say is the symbol for this battery? Because I'm tired of writing it. What do we do with this whole thing here? This is just too painful to write.
Long line to the positive side.
Yeah, so we have a big line here like that. That's our positive side. Negative side?
And then it's short.
A shorter line like this, negative. So this, if I had wires coming out here like this would be my symbol here, and this is going to be a DC voltage source. And DC voltage source, it just means you have a battery. So we do this. Okay, so our electric field is going this way. Here's our electric field. So if you're a little electron, which way do we say you move?
Positive.
Yeah, it's going to go with the positive, so the electron moves this way. So this is the direction that the electrons move. And now here's just where it gets weird. Historically, people didn't think the electrons moved. I mean, now we don't because we have a better understanding of the structure here. But historically, people actually thought positive charge moved. So historically, a physicist thought that the current, that the positive charges moved. So if I had this, same setup, here's my electric field. If you're a positive charge here, which way would you move? Yeah, you're going to move this way. So the positive charge would go like this. So this is the motion of positive charge. Okay, now here's just where it gets weird. Since historically people thought this is what happened, the current would be going this way. That is basically the definition of current. Even though the real current is going to go like this, that's how the electron's moving. When you draw one of these circuits and indicate the direction of the current, you always, always, always have the current as if it were positive going this way. So when you draw the current here, this, you draw the current like I call this I. You assume that the current is positive, even though it is not. And it's just the way it is. Okay, it's weird. So draw the current. In a circuit. As if positive charge. Well, so everything is going to be set up for that. And it will make a difference when we do other things that you have to get the current like that, right? Okay, so that said, let's see what we can do. But here's going to be my little circuit like this. Here's my wire. Call this A. Here's my electric field. Now, before I actually go through and do this I like this, I still want to see what the electron's going to do because we need a little bit more stuff in here. I'm going to say the length of this wire here is L. And this voltage here is V. So if you were to look inside here, what would you do? You'd have all these atoms inside here. So they right here, these are the atoms that make up the wire. Okay, so if you're a tiny little electron here, okay, what are you going to do when you move? Okay, there's going to be a force on you this way. Force on you this way. You're going to move this way, then what's going to happen to you? The electron's going to smash into one of the atoms here. And what's it going to do? It's going to smash into here. It's going to recoil, go like that. The force is still going that way. So it's gonna come back here, it's gonna smash into this one, it's gonna recoil, go this way, smash into this one, recoil, smash into here, go further, smash into here, recoil, smash into here, recoil, smash into here, recoil. And it's gonna hit all these things as it goes along. Does that make sense? So the electron does not travel in a straight line. And we sure in the middle. Okay, it glides with the atoms in the wire. Okay, which impede the flow of the electrons. Okay, we're going to call this impediment to the flow. We're going to call this the resistance in the wire. It's impediment. The electron flow. All resistance. Okay. Actually, now with the modern circuitry, since you can get really these microscopically thin wires, that's actually really important because what happens, these wires can get really thin. Electrons are going through here, and they're actually, when they do these collisions, it can actually take the atoms in here and physically move them. So the circuitry is so small that as the current goes through there, it actually can start physically moving the electrons in the wire, and actually can start causing breaking in the wire, just entirely from these collisions occurring. It's called electromigration. What it's called. It's actually a really active area of research, and it's a very practical point that people have to worry about. You don't really think of this happening. Okay. Can you read this all, or is it all? Question, Mihina?
Did you say that made the wire?
Which part?
That one.
Okay, the electrons that make up the wire.
Oh, okay.
Okay. So let's see what we can do with this here. So I'm going to do kind of a semi-classical derivation for this. Oh, do all materials have resistance? No. Okay. You would think that this occurs in absolutely everything, and it does. However, there are certain materials called superconductors, lead, tin, the kind of poor conductors normally. If you cool them to really low temperatures, like liquid nitrogen temperature, liquid helium temperatures, the resistance in that material actually goes to zero. And then they conduct without any loss of material. That's called superconductivity. The guy who did this is Bardeen. Okay. The theory is called BSC, called the Bardeen, Schrieffer, Cooper theory. He actually got the Nobel Prize for this. Anyone else know what he got the Nobel Prize for? Until very recently, Bardeen was the only person to win 2 Nobel Prizes in physics. One was for the theory of superconductivity. Schrieffer was his graduate student, and Cooper was his postdoc. And they came up with this theory together. Anyone else got the Nobel Prize for? The transistor. Okay, he invented the transistor along with Brattain and Schottky. And so he literally changed the world. He was actually still alive when I was at University of Illinois. He was an old man. But I can tell you my greatness story now. Okay, I had 2 run-ins with Bardeen. It was fantastic. The one, he was in his 80s and I was in my early 20s. One is I was in the bathroom and I was peeing at the same time he was. It was so cool. I was at this urinal and he was at this urinal and went, wow, I'm peeing at the same time. John Bardeen is peeing. It was just greatness. It was just fantastic. The other one is that they have these really heavy doors from going from room to room in the hallways. And then he was in his 80s and kind of shuffled and stuff like this, and I was in my 20s. I opened up the door and I ran into him because I was moving really fast, a lot faster than him, and I almost knocked him on his rear and killed him. There, that's my other brush of greatness with John Bardeen. It's almost like we're brothers, you know. Wow. If I had killed him, that would have ended my graduate career quite soon. He was actually a very nice man. He was a very, very kind and decent man. When I hear people say, well, you know, they did something really important, that person is allowed to be arrogant. I'm sorry, John Bardeen has 2 Nobel Prizes in physics and he changed the world. He was not arrogant or conceited, and I'm sorry. If he doesn't have a right to be, if he's not arrogant and conceited, then shut up, guy. I don't even care what your accomplishments are. Just shut up. You've done nothing. Okay. Once you're done, basically what John Bardeen has done, okay, then we can chat. But until you reach that level of greatness, shut up. You know, don't give me this arrogant crap. He was not like that at all. Okay. Going back to this. So what's going to happen with this? Let's do a semi-classical theory for resistance. Okay, so we're going to do the following. So here's my little electron. Let's see, here's an atom here, like this. And here's my electric field. So I'm going to assume that this is at rest, initially at rest. Let's say assume initially at rest. So the force is on you like this. This is your force. What is the force on that little electron? This is the electric field. How do we define electric field? That's going to be for a point charge. Okay, but so we have this electric field here. So remember, your electric field is a force acting on the charge over the charge. So my force on this little electron is going to be Q times E. Now if I do F equals MA, I can take my little force, put it in here. This is my QE. This is my MA. That's what I have. A equals Q E. We had that expression in lab too. Last time we had that. So what would you call that acceleration? That is, acceleration is an example of a constant. Hey, what do you know when you have constant acceleration? Those 3 equations are valid. So I'm going to say V equals V naught plus AT. So I'm going to take that A and put it in here. I'm saying this is initially at rest. And I'm going to say that time is the time it's going to take that electron to travel from here and collide with this atom here. And I'm going to call that the relaxation time, or let's call it the collision time. So left T, the time it takes the electron to collide with an atom. Let's call this time collision time. Now, what I have here is that this V equals 2E over M tau. So let's say you have something that conducts really, really well. Would that tau be large or small? Let's say it's conducting really, really well. Would you expect tau to be large or small? Okay, that makes sense. Why small?
Smash into the atoms.
Okay, then if it's going to smash into the atoms, what's going to happen? Quickly, what would happen? It smash into here, and then basically have to then smash into here, then smash into here, and kind of get resorted. That's actually going to make it conduct slower. Okay, so if this thing is going really, really low for a long time before it smashes, that's going to conduct really well. So this collision time too, if it's large, is conducting well. Because if it's really, really short, it's smashing into all these things here, and it's not conducting well at all. So the larger the tau, better material conducts. So we're ultimately going to connect basically macroscopic quantities to microscopic physics, which is the wonderful thing we can do these days. Okay. Now let's define something. So we define a new quantity called the current density. J. And J is by definition, it's the current per unit area. So this area is the area of the wire. This is a cross section of area of the wire. Okay. So I want to beat on this and see what that's going to be. So here's our little wire. Here's our A. And here's our little line. So we said this A is a current I. What's the area? What did we say current is? The QDT. So I'm going to write this delta Q just because I'm just going to. They're going to say this is this delta Q over delta T over here. Now, let's figure out how much current we're going to have here. Let's figure out this delta Q. So this delta Q here. Now look at this tiny little section back here. What would be the delta Q for that? I'm going to call this distance right here. I'm going to call that delta X. And this has a section area A. So I'm going to say that this is going to be Q. This is going to be the charge of an electron. Times an n sub E. I don't do that. N sub E. This is going to be your number density. Of electrons. Okay. And then what would I have to multiply that by to get the actual amount of charge in there? What would the number density be? This would be the number of electrons. Volume. I take Q, charge of 1 electron, times the number density of electrons. So this is going to give me how much charge I have per unit volume. What do I then have to multiply that by to get the actual charge in that little region? If I have a number of electrons per unit volume and I just want the number of electrons, I'd want to multiply this by volume. So this has a cross-section area A. This has a thickness delta X. What would be the volume of that little region? I know it doesn't help being 500 degrees in here. It doesn't help anyone think, well, A times U delta X. So what I'm going to do is I'm going to multiply this by A times delta X. This is the volume of the region. The volume of, say, volume of of the region containing the charge. Okay, so I'm going to take that delta Q and put it in here. So my J is going to be my delta Q. I'll write this again like this. So my charge is my buddy here. I divide that by delta T. I divide that by A. What nice thing happens? I think we have some friends here. What are these A's going to do? Cancel. I think delta X over delta T is a friend. That's a velocity. This is my Q and E times V here. Oh, do we know anything about that V? Yeah, we do. We know that this V is that Q, E, M, tau. If I put this in here, what do I get? I get that my current density is Q squared N E tau all over M times E. This right here, what does that? This is just going to depend on the wire. So what we have here is we're going to give that a name. We're going to call that the conductivity. The whole quantity here is Q squared N E tau over M. This is by definition the conductivity. Conductivity, we call that sigma. So what we get here is that we get this J equals sigma E, or better yet, J vector equals sigma times E. If that sigma is large, we have a metal. If that sigma is really small, what's the opposite of a metal? An insulator. What's in between an insulator and a conductor or a metal? A semiconductor. So if sigma is large, have conductor. sigma small. You have an insulator. Your sigma is between. We have a semiconductor. Okay. And with modern techniques, you can just start. With modern techniques, you can get something really, really bizarre happening. Does anyone know what you can get with these? Can you ever have something that's both a metal and an insulator? Actually, you can. Okay, so what you do, you have these materials which are bizarre. And it turns out in one direction, if you send the current in one direction, it can act like a metal. Send the current in another direction, it acts like an insulator. And so you can just get these utterly bizarre materials these days that just have ridiculous properties. You look at it and go, fine, you know, just they're utterly bizarre what you can get. Questions? Okay, one more thing, then we'll call it quits, and then what we'll do is we'll then apply these ideas to lab. So lab, I'm going to hand out some multimeters and some resistors. We're going to do some things with them. So it's going to be kind of combination lab lecture. What would that be for you? Lector? Lector. So that's applied to this now. So here's our little A. Here's our battery. This, and we said this is linked to L. And here's our electric field. That's our electric field. Okay. What did we say is the voltage in a case like this? If we had two plates here, which is kind of we do, when you have an electric field here, which is a constant. Remember how we said that this is really that expression here? Now, what I'm going to do is I'm not going to worry about the minus sign here. Just drop the minus sign. And we're going to drop it because basically we're going to eventually use we're going to assume we have positive current. So ignore the minus sign. And we're going to call the voltage difference here, call delta V, simply V. So I have V equals E times L. Well, I'm going to take this E here, and I'm going to move it over to here. So I'm going to write this as J over sigma L. Well, what did we say is the definition of J? We called it a current density, but what does it equal? Current over area. So I'll put my current over area here. I'll just copy this over here. I'll put my current over area here. That, and I'm going to rewrite this. I will rewrite this as L over A, 1 over sigma. It's kind of fun. Now, 1 over sigma. This is by definition of rho, and this is called the resistivity. So 1 over the conductivity is called the resistivity, and that makes sense. If something is conducting really, really well, do you think it would have a high resistance or a low resistance?
Well,
It'd be low. So if my sigma is large, my rho, my resistivity is going to, if my sigma is high, my resistivity is going to be low. Suppose I have a bad conductor, meaning that the sigma is quite low. This is low, my rho is going to be high. And you would say that then if something has a high resistivity, you would say it actually has a high resistance. So the way we're going to rewrite this is this. So I know this is V equals rho L over A times I. And this whole part here, this rho times L over A is by definition R the resistance. So what we get is this, our famous V equals IR. V equals IR is known as Ohm's law. So that makes sense. If you had a longer wire, what would happen to the resistance in your wire? And why?
Increase.
Yeah, why would you expect a longer wire to have a higher resistance? Exactly, you're going to smash in more atoms, right? The resistance, remember the electron as it goes through and it smashes into things, that's what's causing the resistance. Well, if you have a lot more to smash into, your resistance goes up. Okay, why would this go as 1 over the area? It says if I have a bigger cross-section here, I have a lower resistance. Whereas if I have a smaller cross-section, I have a higher resistance. Why might that be the case? Basically, if those particles are spread over a bigger area, it's going to be easier for that electron to kind of snake through. In which case, if it can go through easier, you can actually have a lower resistance. Whereas if it's really, really narrow, then what's going to happen is you're going to be bumping into things all the time, in which case the resistance is going to be higher. I was doing a lab, so my first position was because I was new, and the new people get crap. Okay, they gave me a class basically teaching basics physics to these education majors. We had a lab, and this is almost verbatim what happened. The lab was just this. You basically had wires of different length. And the whole point of the lab was to show that as you had more length in the wire, the resistance went up. And there was a question in the lab. There was a resistivity table. So they gave a whole bunch of resistivity values. You can look up the value. There's a question that said, what wire makes the best wiring for a house? What is it and why isn't it used? And all you had to do is you looked up this, find the smallest row, and write it down. And it was basically gold, and you don't use it because it's too expensive. And these two lab partners working together, this almost destroyed me. This is almost verbatim what they said. It might even be verbatim. They said, blood makes the best wire for a house. We don't use it because we need it to live. And you're at home and you're reading this, and you realize that they said blood. And you read it again, and it still says blood. Okay, so you just kind of go to the refrigerator and you open up the refrigerator and grab a bottle of beer. And you just take your little bottle of beer and you hop in bed with your clothes still on, and you just sit in like a tight little ball in the middle of your bed. And you pull the sheets over your head like this while you have your tiny little bottle of beer. And you just stay there for the rest of the day because basically your brain is starting to be shut down because you just read that somebody said that blood makes the best wiring for a house. That almost destroyed me. But I survived. Okay. See you later this afternoon. Have fun.